So I used it last year very little, but now I'm using it all the time. So I'm running a whole stellar structure and evolution course, doing all derivations like that. And then I do some Q&A on Zoom. So it's all right. I mean, yeah.
Well, we're doing okay. We're up to 22 people.
So here we're recording this. Are you going to?
Yeah, so I'm going to record it and provide. A couple of people have asked who couldn't make it today. So
it's not that good.
No, it's very straightforward.
Are you in Greece, Johan?
Yes, in right.
They're streaming in.
Oh, yes.
There's Gabby. She won't remember, but
yeah, that's me, and I do remember you.
You do remember that? Doesn't sound amazing. You know, when you finally did the detection, we showed the video that we did all those years ago. And it's funnier, you might not know, but Mike Zucker's brother, Dan, is here at Macquarie. And
that's
in fact, 10 years ago, we both arrived together, and I looked at him, and I had interviewed Mike a few years earlier, and I was looking at Dan and looking at the name, and I'm thinking, have I met you somewhere? Your name, your face? And then and Mike has visited a couple of times, so it's been wonderful to see him.
Yes.
How many people?
We've got 39 people.
40 now, yeah.
And there's Ardo too. Well, I'm gonna have to visit before January, Jeff, because the airline gave me a credit, which is like a voucher.
Okay, well, yeah, come anytime.
I didn't know that. Although I think Australia and many countries will reopen, will just go out of lockdown sometime soon, but internationally is going to be really tricky, right? So who knows?
Yeah, I know. They're not going to just allow people from the US to come, or you to come to the US.
Or to come back.
Yeah, or come back. Well, you have to go into quarantine for 14 days or something.
You see, I have 2 passports. They can't stop me.
Yeah, I've got 2 also.
Well,
You've
I've
actually got 4.
Between Australia. So, but they can put you in quarantine for 2 weeks, of course, both ways.
Right. Yes.
So I can come for 2 weeks, but I have to do a month of quarantine, grand total.
Right, exactly. Okay, so we're just going to wait a couple of minutes for people to come on. It's just 3:30 now. It's 6:30 a.m. in Australia.
So thank you, Ursula, for getting up so early.
So I think if I hear the kookaburra, I'll stop a second. I'm like, because they really start singing as soon as the sun comes out, which is not quite yet. It's really amazing. It's really loud.
That's true here in Louisiana too.
The birds when the sun comes out. Yeah, it's just.
But Australia does have the loudest birds in the world, I think.
Oh my God. When I've guessed it's the first time, they wake up and they come out and says, "What is going on?"
Okay, we're just going to wait one more minute.
I actually have a photograph of Noam in this talk.
Yes, we can do it before and after.
It's my photo's definitely before. He'll be happy because I really credit him.
Well, yes. We're up to over 50 people.
I'm shocked.
I think we're having more than a normal colloquium for sure.
I was thinking the same, but I'm not sure that's true.
Yeah.
Well, okay, but it's
At least the colloquia I go to, which is not all.
I think we're getting up there though. Okay, so I'm going to mute everybody for the talk. I'd like everyone just to hold their questions to the end. We're going to have lots of time for Q&A, and we also have a half an hour from 4:30 to 5 after the talk if you want to stick around and just chat with the speaker. And then for grad students, there's going to be a separate Zoom on a separate Zoom number for the grad students to talk to Orsola. So our speaker today is Orsola De Marco. She's a professor at Macquarie University in Sydney. She got her PhD at University College London, and then did a postdoc at the ETH in Zurich, and then came back for another postdoc at UCL, and then moved to New York City to work at the American Museum of Natural History, and then went to Australia, where she's now been for 11 years. Yeah, I know. So I'm just going to pass it right over to you, Orsola, and have a good time.
Okay, so I'm gonna screen share. Where do I do that? Here. And I hope there's also a movie which so I'm sharing. So do you see the regular presentation?
Yes.
Great. Okay. So hello, everybody. It is really sad not to be there. I was going to be in Baton Rouge for 2 weeks around Easter. But hey, we do what we can. So I'm going to give, so as you can imagine by my advanced age, my talks are now, you know, there's lots of talks that I give and they're all pick and mix and, you know, and I put together something that is pretty much my recent work. However, it is very much contextualized on the common envelope binary interaction problem, which when I started was really something that seemed to interest only me. And I liked it because of planetary nebula, and I'll show you a little bit of that in a second. But now it has become really, really a fundamental problem to solve. And in fact, it's really nice Gabby's here because it is being connected to gravitational wave and to the merger of any types of stars, from the very interesting and exoteric black holes and neutron stars to the more mundane white dwarfs that create things like type 1a supernovae. So, and they're being created and they're being connected due to this relationship I'm about to show you. And I call this the problem we used to have solved, because when I started this working in this field about, about 15, 20 years ago, the literature that I could find on the common envelope seemed to say, well, we kind of simulated it and we kind of know what's going on. And I definitely think that through my work and the work that's going on more recently now, we definitely think we have not even touched the solution. So let's get going. So as usual, I have a little outline, and I'll start from planetary nebulae because they're interesting, because that's where I started from, and because they really show a lot of things about the common envelope. I'll talk a little bit more about the astrophysics of the common envelope and the various bits in it that are complicated, and the simulations we've carried out of it. And then a little bit about why they're so interesting and important to solve right now, as they're connected to all kinds of transients, not just the gravitational wave transients, but also, of course, the electromagnetic radiation transients. And finally, I'll go crazy and I'll talk about nebulae and jets, which Noam will be, I'm gonna get some kudos here from Noam. And in fact, I'll talk about a paper that Sagiv did, which is crazy, putting jets in common envelope like we don't need anything else. So let's start with planetary nebulae. They are nebulae formed by stars like our sun. And on the left side, I have a little diagram that shows luminosity versus temperature. It's called an HR diagram. It's a staple of stellar astrophysicists. And in there, do you see that? You do. We see how stars get bright and big and lose most of their mass towards the top right of that diagram. And the mass that is lost is eventually ionized, shines as a beautiful nebula. And you see a bunch of examples here on the right. Now, why do this nebula have this? If you look here, they all have amazing shapes. They have very, very elongated ones, and even the ones not elongated, elliptical. And for the longest time, it's not being clear why. But when I started in the field, I got my PhD in '97 working in planet nebula. There were papers such as this one and some precursor of it that explain every shape there is. And as you can see here, these are theoretical maps of all kinds of shapes of planetary nebula. And all they said is it's easy to explain the shape. When you lose mass, you do so in equatorial donut. And then the mass that comes out after that is squished by the donut and comes out in an elongated shape. Very easy. However, these two guys at the time, and in fact before that, had been saying that this doesn't make any sense. First of all, Noam on the right here seen at an earlier epoch, had theoretically shown that it actually is much more plausible that the shapes are created by a companion that is present at the time of the mass loss and the nebula loss. And on the left, Howard Bond had actually been observing a lot of these shapes. That no one can.
Can everybody turn their video off, and if they haven't already?
That a part of the binary was in the mass.
Stand by. Orsola, are you there?
Can you hear me now?
Yes. You might try to just turn off your video.
Turn off my video?
Yeah.
Sure. Okay. Am I good to continue?
You're going to have to share screen again.
Oh, really? How odd. Okay. I think I don't hear you while I share screen for some reason. Well, if there's anything that matters, just text me, okay? So this other paper basically said the same thing. And it was at that time that the entire community realized that unless you have binarity, you're not going to explain planetary nebula shapes. And in fact, since most planetary nebula have odd shapes, it seems like binarity is very pervasive. Now, we know there's also non-binaries out there, and those perhaps make either subluminous or even inexistent nebulae. Let me see if okay. So how do you, the first thing, of course, if planetary nebula are primarily or dominated by binarity, how do you find the binaries? That's the first thing you're gonna do. And it turns out that when you have a closed binary inside a nebula, indeed any closed binary, you have three effects that are quite obvious observationally. On the left, you have eclipsing binaries. Obviously, you see in the light curve, you see the eclipse, where periodically you see a diminishment of the light. You can also see variability due to an effect called as known as ellipsoidal variability. And that's basically the two stars are stretched by each other's gravity. And when they present the side view, there's more light. And when they present the head view, there's less light. So you see variability. And finally, it turns out that if one star is hot, like the central star of Planetary Nebula is basically a white dwarf, and the other one is a kind of a boring main sequence star, you can irradiate one side of the main sequence star, and that side's brighter. And as you go round in the orbital period, you can see variability as well. People looked for we last 20 years we've been finding binaries that way and finding that central star or Planetary Nebula with binaries are at least 1 in 5. It turns out that's a very hard limit, so it could well be 1 in 3. Now, how do you make when you know binaries we find are these effects of variability? How do you have a short period binary, a very compact binary, when you want to system perhaps been giants in the past? Basically, the orbit is so teeny today that the stars must have been inside the progenitor of the evolved star in the past. So, this is a project much earlier, Minsky in 1967, when he had realized there's a hell of a lot, not just central stars of Planetary Nebula, where there are 1 or 2 evolved stars in close orbits. So it turns out this idea that you have a binary, then you have the growth of one of the 2 stars, it envelops the entire orbit, and then the orbit shrinks down to what you see today, had come to Paczynski, and it can explain things like double neutron stars, potentially some double black holes, double white dwarfs, white dwarf main sequence stars such as cataclysmic variables, the central stars of Planetary Nebula was discussing, and indeed the progenitors of things like type 1a supernovae and many types of transients that are the product of merging stars. So now we're going to concentrate on this phenomenon that shrinks the orbit when one of the 2 stars grows. Can't just be finally missing the famous gesticulation of Orsola. What is that mark? Anyway, I'm going to show you the movie if I can. So what I have to do, I have to find the browser. Show you this movie. It's a little bit long and I'll chop it short. But my former PhD Thomas Reichardt about one of his simulations, and it captioned for public. It's much simpler, but it explains what the common envelope is. Okay, I'm gonna stop this and go back. So the point here is that, and I'm diagrams. So this, by the way, apologies for the music. The reason for it is that Thomas entered for a competition in Australasian Dynamics Society, and he actually won it. And I think it's thanks to the music, which I added for him because of a long movie. Anyway, you kind of catch the idea of this about the interaction in general. So you see on the left this diagram where you have the two stars revolving around another. The figure of 8 is what's known as a Roche lobe, which is an equipotential surface around the two stars. One of the two stars expands on the top right and fills its Roche lobe, at which point material moves to the second star, creating a dip. Depending on how fast this material goes through L1, you may go through this, go from stable to unstable mass transfer. There is mass loss through the L2 and L3 points on either side of the two stars, and eventually the whole thing is inside a common envelope. When that takes place, the core of the giant and the companion spiral towards one another, reducing their orbit greatly. Now we simulate this either with the grid codes or with a SPH code, which is the case for the simulation you've just seen earlier. And at best, we reach resolution of a fraction of a solar radius. This on the right is pretty much the idea of the simulation. You have either a box in a SPH, you don't have a box, but give or take, it's the same idea. The box is about 250 solar radii. That symbol stands for solar radius. Typically, we simulate low mass stars. So we have one solar mass, like the sun in its future, when it's giant. The core is about half a solar mass, the envelope is another half solar mass, and the companion is give or take another half solar mass. The period initially is 1 year, and then we just put them in orbit. You go through the Roche lobe overflow, which you've seen in the movie, and then through the common envelope. Now, as I showed you before, the star expands, so I put here the whole screen is red because the star core, the core of the giant and the companion approach one another in the spiral. And eventually, after about something of the order of dynamical time of the star, which is of the order of a month, in this case, the core and the companion really close to one another, as you can see here, the order of 2 radii. And a lot of the material of the giant star has expanded, and in theory, it should be ejected if the core and companion are to survive as a binary, the binaries we observe. Now, before we get to the punchline of the common envelope, does the binary survive, you get a merger, let's talk a little bit about how it works. Why do you get the spiral in the first place? Right now, in this diagram here, which I think I stole from the internet somewhere, you see a body moving in fluid that represented by little particles. And of course, it attracts them. And as the body moves, it creates a wake behind it. And this wake is dense and alters the motion of that body, slows it down. And if it is in an orbit, it deorbits it. Now, this is known as a very quick explanation and quite partial gravitational friction, and can be represented analytically with the first expression on the right, where basically it says that the gravitational influence of the body on the surrounding material changes the motion of the body, and the body feels a force, which we call the gravitational drag. It is very similar to the hydrodynamic drag that you experience if you're, say, wading in water, where the hydrodynamic drag is due to your leg, so the area of your leg hitting the water, whereas the gravitational drag is a bit more. It's due to the, in the case of your legs wading in water, is due to the gravity of your legs on the water, which of course for legs wading in water is very small. But if you have a star inside a star, its gravity is even more powerful than its physical presence in the gas of the star, and creates a force. So this force is the source of the inspiral that you observe. Now, we spent many years trying to understand whether the simulations can reproduce this effect correctly. And in fact, it has been a semi-obsession of mine in every time we do a simulation to try and understand whether the forces that my body is experiencing in the simulation are correct. Now here we have in black the in-spiral, so this is a radial distance from the center versus time, and on the right, on the right axis is in-spiral, on the left axis you see the forces that the in-spiraling body perceives or feels. And in blue, it doesn't matter light or dark, you see the forces that we know the body feels in the simulation. And the green is the same. And the red is the analytical expression, which we believe should be the actual force that the body experiences. And you see a mismatch, but it's not a big mismatch. It's actually, this is a linear scale, it's not a log scale. And in fact, there are reasons why there are this change in the peak, but I'm not going to go into these details. But the bottom line is, in this paper, we show that we think we understand the gravitational friction, and we think that the simulation, even with all its shortcomings, is doing an okay job on it. Now, there are other issues when you simulate this type of interaction. And one of them is that stars are really complicated objects. Here we have in blue a profile of density, pressure, and so on, and other quantities of a star calculated by a 1D code. 1D codes can do great jobs at calculating stellar structures. The problem is once you try and reproduce the information into a 3D computational domain where your resolution is far worse, you cannot map the star accurately enough to even call it a star. So what you see here in black, magenta, and green are 3 different resolution mapping of that blue profile inside of the 3D computational domain. That was of an SPH code we used to use a while ago. Now, as you can see on the left, the core of the star, this is a log x-axis. So the core of the star is not represented very well. You cannot do that. You don't have enough resolution. The cores are tiny in these giants, and you just cannot do it unless you want to wait, I don't know, a century for your simulation to run. Now, as a result, we substitute the core material with a point mass. A point mass is a mass that has mass, but it doesn't have width, doesn't have a body. And so the potential can be represented accurately, but of course it's not gas. It turns out that in giant stars, where the giant has such a really compact P of a core and around is such a massive, gigantic envelope, it's just about a good enough approximation. Now, the P in the middle, the point mass, has of course a potential that's an R to the -2 potential. And as you get close to the point mass, you get an infinite potential. And of course, we can't have that in codes. So we soften that potential with some function. And that itself is another source of uncertainty in simulations. So I am quite critical of simulations in general, despite having done them for quite a long time now, because one has to really not trust them too much. In fact, people who simulate who are not very critical simulations I really think should not be trustworthy. You really should be super critical because there's a lot of issues. Here on the left and right is the plots I've already shown you. And in the middle is something from Thomas's thesis where he shows you a slice of a 3D mapping of a star in the computational domain. On the top left, you see how geometric it looks. Of course, that's because there's an algorithm to place your mass representing SPH particles within the 3D domain. Then we relax the star. We have techniques to make sure that it's in hydrostatic equilibrium and that its density profile is approximately what we expect for a star. Otherwise, you don't have a star at all. And with that, we then use the companion to put in orbit and start a simulation. Now, simulations such as these were started in the 70s by, I guess the pioneering group was Ron Town's group at Northwestern. And since 1978, in a series of papers, which were really amazing papers, I still go back and read them today, they just basically did a bunch of common envelope simulations. And he was certainly the primary one. And then there's this interesting simulation by Razi and Livio, also with an SPH code, that pretty much set the stage. And when you read those papers, although they do talk about the caveats and so on, you do get the impression that we kind of understand. We understand the gravel drag that drives the interaction, and you understand pretty much everything about the simulation and potentially the interaction by extrapolation. Now, before I tell you the but, let me tell you what people have been looking for by simulating this common envelope. So on the left, we have a cartoon of the giant and its companion that's just starting spiral, and there's this little light blue line that shows you the spiral that's going to happen. The separation between the two reduces, as you know by now, and eventually, if you eject the gas, you end up with a short period binaries, the one I look for in the middle of planetary nebulae. And the final separation is actually the key, is what we are looking for, is the holy grail of doing all this work. What you want to know is the final separation of each binary, meaning the final separation as a function of initial separation, the masses, the evolutionary stage of the stars, and so on. And the reason is because by knowing the final separation, you predict what's going to happen next. For example, if the final separation is teeny, 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 this guy's going to merge and give you maybe a type 1a supernova or a gravitational wave explosion very quickly. But if that final separation is wider, you're going to wait a long time. So the delay time between the common envelope giving you the short period binary and what happens next, the next phase, which we also observe, depends on this final separation. However, this final separation seems to be extremely elusive, and certainly simulations have not successfully given it to us yet. Now, this is just a little aside. The final separation as a function of all other parameters is what population synthesis models use in order to understand how whole populations of binaries, the massive ones, the intermediate mass one, the low mass one, the one that give you gravitational waves, the black hole, neutron stars, population synthesis model give you the whole idea of how these binaries behave as a population. And on the right here, you have a typical diagram that these papers produce where they give you all the stages in the binary life, and the two underlined in red give you the common envelope phases, which in this case was twice in the life of this binary. And you see how the 318 separation goes to 5 in the first common envelope, and the 5.6 separation goes to 5.5 in the second common envelope. And that reduction is what drives the entire evolution of the system. And that reduction in separation is what we don't understand very well, and what we're looking for to get with these simulations. Okay, this is maybe, again, still part of your slide, and I'll go quickly. It's not that important. I could have taken this out. But the bottom line is that the way this population synthesis computations work, they don't have time to simulate everything, obviously. The simulations take a very long time on supercomputers to complete. So the way they do is they parameterize it in a very simple way. And on the top equation, you have the binding energy of the envelope of your giant. And on the right-hand side, you have the delivered orbital energy delivered by the orbital shrinking. And basically, you balance out the two with this alpha, which is an efficiency parameter. Now, it turns out that that alpha, if you use a very close number, very close to 1, is going to give you a very different final separation. On the bottom equation is the same as the top equation, where we're spelling out all the terms and factors. And you see how the delivered orbital energy is the final orbital energy minus the initial orbital energy. And the final orbital energy is what contains that final separation I was talking about earlier. So basically, the population synthesis want to have the alpha because they need to use it in their simplified equation. Whereas from the point of view of the simulations, what I do is I know the final separation from my simulation, and I could perhaps derive the alpha. So the simplistic view that I had about a decade ago was easy. We're going to do lots and lots of simulations with lots and lots of parameters present in this second equation. And I'm going to look for the final separation in each of the simulation, and I'm going to derive this efficiency parameter that then the population synthesis model can happily use. And I have solved one of the biggest problems in binary evolution. So that's what I said here, basically. So we know everything in a simulation, and we can derive alpha. So I started working with this, and I did so with a code which actually is used for cosmological simulation known as ENSO. And we did a paper which came out in 2012 with my first PhD student. And in this paper, we were just going, every time we discovered something, we're going backwards. And so what you see here is basically that paper had a bunch of simulations of the same giant with lots and lots of different companions with different masses. And what you're looking at here is a separation versus time, which is basically the in spiral of your object. And you see how each of them levels out to a certain separation, which is your final separation we were looking for. And so you could say, well, yeah, you cracked it, right? You got all these final separations as a function of the initial parameter of your simulation. You really are starting to get that grid and create that function. The problem was, in the same paper, we could demonstrate that although the separation levels out and the envelope gas has been expanded, it actually hasn't been ejected. On the top diagram here, you have the escape velocity from the core of our primary, of our giant. And on you can also see the gas velocities towards the end of the simulation. And you see a lot of the gas is now at higher than escape speed, and this gas has been ejected. But also there is a little bit of gas below that line. If you go to the bottom panel, you see that at a radius of about 1,000 arcsun, there still is 0.9% of the envelope. What that tells you is that 90% of the envelope, although it's expanded, it has not been ejected. So if you don't eject the envelope in your simulation, then the envelope presumably will come back and it will go back to making a star. And you haven't emerged as a binary, because you're going to go back and you're going to merge the binary in the common envelope. And it turns out that this is now the single biggest problem in common envelope simulations, is that no simulation, except something I'll tell you towards the end, can eject the envelope. So this is a little table that shows you, this actually I did a bunch of years ago, and there's a lot more simulations today. This is a bunch of simulation. The bottom line there tells you the unbound mass. Remember, in order to save the binary, give you the final separation, you have to unbind pretty much all the envelope. But this simulation unbind at best 30%. What's going on? What is wrong in the simulation? Or are we, what? See 2030. Created one, and it's really because in his paper you really outline the issue but been evident in previous papers enough to say, look, we will nothing until we can eject the envelope. There's been a bunch of others, and some of them, like from my group and Natasha Ivanova in Canada, have been concentrating on how do we unbind the envelope. Now, Natasha originally found that if the envelope expands, there's no again on the bottom left, by the way. So if the envelope expands, gas recombines, particularly on the outer layers, and that means that recombination photons are emitted. And if those photons can be thermalized locally, then they translate that energy into work and expansion, and it turns out there's plenty of energy to eject the envelope. This had been suggested a few years earlier, but Natasha was the first one to put them into the simulation and actually notice that you can unbind a lot of the envelope if you account for the recombination energy. Now, there's been a series of papers, like a to and fro paper series between Natasha and Noam, where Noam points out that when you recombine, the gas ahead of the recombination front becomes transparent. And that transparency contributes to losing the very photons that have to do work, that have to expand your envelope. So you effectively, you want the pressure, but you're actually degassing the pressure out because of the transparency of the medium. It turns out that I tend to, in this case, agree with Noam that a lot of that energy is ejected, because there are some observational reasons to believe that. Now, first of all, AGB stars, these giants that lose mass, also pulsate. And as they pulsate in and out, they actually unbind a lot of gas. Now, if recombination energy were that efficient, those AGB stars would actually undo themselves very quickly. They actually do, but not quite that quickly. There are other reasons to believe that the recombination energy actually comes out and doesn't do work and expand and eject your envelope. In common envelope transients, which we have observed some, we see radiation that comes from the recombination front. If you see it, it means it's coming out. It also is noticed that in certain types of transients, the spectrum shows you this emission lines developing during the outburst. And these emission lines show you that the gas that is creating those lines is really fast, well above escape speed. That means that the gas has already been ejected by potentially something else. So there's a lot of reasons to believe that the recombination energy perhaps helps the ejection of the envelope, but it is not the whole story. That this year, rates and time on the decline is once again. We have this, we call it the passive simulation. On the top part of and what you see in this
Stand by. You there, Ursula? Ursula, can you unmute?
You may have to send her a text.
I don't know why I can't unmute her. Yeah, I don't know why this isn't, I can't unmute her.
You can see that she's muted.
Yes.
And you have tried.
Now you are.
Okay, now the question is, what are you seeing? Because wait, share. It seems to break every time it joins.
Are you still there?
So, can you hear me?
Yeah, you're breaking up though. Well, this is working so well for a while.
Yeah.
Do you Do you see my screen?
You need to share it again.
And you see now, right?
No.
I don't hear you anymore.
Well, I can hear you, but we're not seeing your screen.
What are you seeing?
Okay, it's just coming on now.
I think the bandwidth is just not very good.
Okay, so I'm just gonna.
There it's back. We can see it now.
So the point in relation. The departure of energy. A little, if it could work type thing. So here we, as usual, from large distances to small distances. And interestingly, in narrow energy,
We are losing the audio again. Yeah.
Yeah, she's getting the spinning wheel on her end. Stand by.
Technology is great when it works.
Okay, so Orso's going to talk now. Can you hear her?
Hold on a second.
Briefly.
Okay,
Can you hear me?
We can hear you, yes.
okay, go ahead.
So I can just, I'll wrap it up visually. Although what I could also do is try again, but anyway, so should I do that?
Yeah, just, you can try and restart it, but go ahead and talk while you're doing it.
Okay, so basically, I mean, I was getting to the punchline of the simulations, despite these efforts, which have now gone for basically 2 decades of the modern efforts, but really, if you go back, add another 2 decades, I can't say they come out to nothing, but definitely we now know how very, very, very difficult it is to do the simulations in a predictive fashion, given that the resolution that we can reach in reasonable simulation times is just not very good. And these simulations, if you go to the higher resolution ones, we're talking about a year on a supercomputer. So they're really, really long. So the bottom line, I think, is that we probably can make these things efficient enough. And part of the work with LSU, with Dr. Tiger that we're doing now, is about gaining maybe an order of magnitude in wall clock time reduction. And if you do that, then perhaps you can start putting sufficient physics and enough resolution to help you out on this. Now, the next part of the talk, which is very little, was actually talking about some crazy experiments we've run, which are basically a mix of simulations and observations. And it's kind of the fun part of the talk. You know, sometimes when you're banging your head against the wall for 2 decades, it kind of is not fun anymore, right? And actually, I'm a bit negative about simulations, but actually it is banging your head against the wall, but it is also very important to continue in that direction. And so one of the things that is also fun to do is perhaps some of the avenues that Noam, who's listening to this talk, does follow, and that Sagiv has done as well. And it is to try and see other things. So one of the issues, maybe I'm going to try one more time, guys, and if you bear with me. Okay, so I'm going to put my phone down for a second, Jeff, okay?
Okay.
Orsola De Marco.
Okay, we're back to you.
So do you hear me on the Zoom?
No.
Okay, it seems like my system seems like it's absolutely normal and I'm not muted.
It just says connecting to audio.
So it's just got a delay. Okay. So Jeff, I think the best thing is that I kind of wrap it up and cut it a little short. Yeah.
Well, and then we can just take questions.
Okay, so let me just finish this one thing, and then we can just do some questions. Basically, the heart of the talk is done. The fun part was coming. So I was just going to describe. You know, I told you how hard it is to eject the envelope, and actually, Noam a while ago with some of his students had this really good idea that perhaps if the companion accretes mass and emits jets, then perhaps those jets could move energy around sufficiently to unbind part of the envelope. And so Sagiv actually was the lead in all this series of papers, one of which I was lucky enough to be part of, where we actually used ENSO and our simulations of common envelope with the addition of jets coming out of the companion that is in spiraling. And what we found is that if this were to happen, of course we don't know because the jets are kind of put in the simulation ad hoc. If this were to happen, you might get another 20% of envelope ejected. Okay. It's being recorded. So Jeff, I'll continue on the phone because the Zoom is working now, but it's super. Oh, now I'm hearing it. Wait a second. So you can hear me on Zoom now, right, guys?
No.
but I don't hear you.
Okay.
So, okay, let's just.
Okay, go ahead, Orsola on Zoom.
Orsola De Marco.
Go ahead.
So let's abandon Zoom altogether. So I've tried now 3 times. It connects and then disconnects immediately. So, let me just wrap it up, okay? So there's a lot of things that we tried out as experiments. For instance, whether, remember we started talking about planetary nebulae, and we know that there are post-common envelopes binaries in the middle of planetary nebulae, and we therefore know that those nebulae are the common envelopes, are the ejected common envelope. So we started looking to see whether we could reproduce some of the nebula properties and shapes, and this experiment has been very successful. We have 2 papers out that show how well this works. Of course, it also shows problems, but it also shows how the nebulae themselves are observable that you can use to corroborate some aspects of the simulation. And the final thing that we did do is actually looking at jets in planetary nebulae, which sometimes you see for some of the objects, and use the properties of those jets, which are connected to the binaries in the middle, to understand what happened in the common envelope. So you have a lot of observational tools that you can mine out of the huge vast sea of observations that can help you to understand this interaction, not just the simulation you just carried out. And of course, as I said, thanks to the work at LSU and not exclusively, we can make the simulations better, faster, and more accurate. And that is where we hope, think a lot of the advancements in binary interactions will lie. And I think with this, I should really stop.
Thank you. We're going to take some questions. If you want to ask a question, please hit the yes or the yes, or put your hand up. And then you can unmute yourself by hitting the space button. So Gabby, try asking a question.
Hi. Sorry, we couldn't see all the movies and the slides. When we, as you probably know, when we began detecting more black hole binaries than people suspected there were some papers saying that this was due to the common envelope, and I'm speaking out of ignorance here, so I'm asking you as the expert to correct me, that this could be due to the common envelope keeping binaries together, even though the supernovas explode and the stars explode and make everything go away. Do you have an opinion on that?
I could hear only part of your question, but I think you're saying that there's more black hole binaries than perhaps anticipated by some models. And so the idea is that, well, there must be efficient common envelopes that get ejected but leave behind the 2 stars, despite the fact, of course, black holes go through, if they're stellar mass black holes, they go through a violent history, including supernovae. And of course, we know that sometimes supernova kicks eject a companion. So to be honest with you, not being an expert on massive stars, I really don't even start knowing what happens in the whole evolution of a binary, including its common envelopes, when you have supernovae as well in there. But ultimately, the common envelope, it can only do 3 things. It can bring the binary together and leave it as a binary, bring it together more closely or less closely, or just merge it into one, right? So playing with those parameters, you can, at the moment we don't know exactly which parameters give you which outcomes. And so that's what population synthesis do. They just play with the parameters until they get the outcome they want. For example, a higher rate of black hole mergers. So I'm not sure what I think of that.
Thanks.
Any other questions?
Yeah.
Go ahead.
Okay. Hello, Ursula. V1309 SCO is the one well-observed common envelope merger system, and it can kind of serve as a huge analog computer simulation for you. For example, people probably have already gotten out that alpha subcommon envelope, the common envelope efficiency for that one system. And I know that you and Kundan and various people in the LSU group have gone off and looked at V1309 SCO. What can you learn from that? I actually don't recall from Kundan's talk from years ago.
Well, the problem with alpha is that alpha shows you the efficiency of ejection. Now, the V1309 SCO was a merger, and so clearly that ejection didn't work, right? So this V1309 SCO was a merger of about 1.5 solar mass subgiant with a 0.1.2 solar mass companion. Now, interestingly, and it was merged at a very early time. So the main star was becoming a giant, but it wasn't very large yet, which means its envelope was very bound, right? So it's hard to eject more bound material. As a result, it ended up in a merger. I have actually tried to simulate that, but we don't have the tools for simulations of stars that are that compact. This is more a job for tools that can do, say, main sequence mergers or wide dwarf mergers. But the bottom line is you don't have the alpha from that because you're not successfully ejecting the envelope. And you just know, you're right, it's a point on your parameter space that a point, 1.5 solar mass subgiant star with a companion 1/10 the mass of it doesn't survive.
Okay.
Can I make a comment?
Yes, go ahead, Johan.
The case of V1309, I think, is very different from the standard picture of common envelope evolution, because it is driven by the Darwin instability. It does not really require a medium against which you have to have dissipation and friction. And ultimately, in the case of V1309, unless we were to see mass that is left behind as an envelope, it clearly merged, and we don't care whether the envelope was fully ejected or is still hanging around. I mean, there may be some observational signature there, but what I'm saying is that you really, I don't think, can use V1309 as a means of determining alpha or alpha and lambda or whatever the combination of those two parameters is.
Gotcha. Johan, could you tell us observers what the Darwin instability is?
Well, when you have a very large mass ratio between the smaller object and the bigger object, then you get to a situation where the only way you can reduce the angular momentum of the orbit is by spinning up the components of the binary, getting them further out of synchronism. And so then the tides try to synchronize, which then robs even more angular momentum, and the process is a runaway.
So, but the Darwin instability is certainly the beginning of the process, but then the later part of that merger would have been a common envelope merger. The two would have gone together and disrupted one another. But again, you can't do the alpha unless you have a binary at the end of the story, and you don't here. You have a merged star. Right.
No, you're right that in the end you have a small star entering the envelope of another one.
Yeah, it has to.
It's not, because they're both, at least the engulfing star is a main sequence star. We're not dealing with the tenuous atmospheres of giants.
No, that's right. And also the other thing, and the reason why I tried to simulate this and then I gave up, is that much of what you want to model in this object is the phase before you get the poof, the merger, and all that phase
Right.
is dominated by the Darwin instability, by lots of mass transfer, a very initial mass transfer, and you have the L203 outflow, and so that is in a way, it happens also in giant common envelopes, but is the pre-common envelope phase, which is itself very complex, and that's one of the questions we also have. We never really give much time to what happens before the spiral. And that before may matter as to what happens after. So that's something that I've been devoting quite a bit of attention, but it is very hard to do in simulation. So the V1309 SCO, there are some simulations out there, but they're either, it's interesting, so there are common envelope simulations for the type which are not, they're not very good, but there's also some simulations of the pre-phase.
Right.
Sorry, I can't hear that.
No, I was saying, as you know, we're trying with Octo-Tiger, but so far we don't have a
but the thing is that, yes, it's the pre-phase, and it's really dominated, the light at least is dominated by a complex circumstellar behavior of the streaks that comes out of L2 and L3. So that is a question of also modeling the light in gas that is both optically thick and optically thin. So it's pretty complicated.
Yeah, I agree. That is difficult.
Any other questions?
Jeff?
Yes.
Emily has a question.
Yeah, sorry, we're sitting here together. I have a question though. So the outbursts that you mentioned briefly, are they accretion outbursts?
So, well, outburst is a word that I use very loosely. You think, what do you mean? When did I mention it? The outburst in, so you can call it, common envelope mergers have a light outburst, right? Now we know there's been observations of, like V1309 SCO certainly is one of them. There's been another one in the galaxy, BA3A monocerotis, and there's been, of course, several extragalactic one, maybe a dozen. And yeah, so the outburst is basically conversion of gravitational energy of mass going towards a central potential into kinetic energy and then eventually light.
Okay, could you give me like a ballpark on what the magnitude of the increase in luminosity is for those outbursts?
So we know from V1309 SCO actually is a good example because it's in the mass range that I usually take into consideration. That was, maybe Brad knows that better, but it was like, it went up by 6 magnitudes, something like that.
Wow.
But
Cool.
this was a low mass one, right? So it's a mix of the mass and the compactness, right? For how much or how much gravitational energy you have.
Mm-hmm.
So this was a low mass, but it was compact. If you had a giant like the ones I simulated, it would be less bright. But this was a funny paper. I had a paper at some point where I was trying to do the light properties of the simulations, and I therefore gathered what we knew at the time, which was a few years ago. And so there's a little table there of all the ones that I could find in the literature at the time, which was like 5. And I can send a link.
Yeah, please, that would be really cool.
In fact, I had a slide on my talk, which is from a paper of Nathan Smith, I think. It was just one that gathered all the, so I'm actually looking here. There were lots of them, including more massive ones. So the V1309 SCO we're talking about, it's always of the order of 5 to maybe 8 magnitudes. And that's when we know the precursor's brightness, right? Sometimes we don't know. So we don't know how dim it was before it had the outburst.
Mm-hmm.
So Smith et al. In 2016, there's a really nice picture with all the light curves known at the time.
I think that paper also has Jen Andrews, who's on board on our Zoomokium here. I think she was a co-author on that too.
Yeah, and what we found is the more massive the star, or like for NGC 4 5590T, which was an LBD that we think was a merger. Your absolute magnitude, it gets to about -14 to -15, so a little bit sub core collapse supernovae.
Yeah, and those were massive stars, so that's good. And I have here another one, which was the M31 LRN 2015, which was probably a pretty good common envelope example. And it went from -5 to -10, so it's a 5 magnitude jump. But I don't think they had a good idea of the precursor in that case, so it would have been more than that.
Makes sense. I mean, if you're starting out with a more massive star, then you have more gravitational energy to transfer into other kinds of energy to make the outburst brighter.
Yeah, so you pretty much know that, it's a gravity-driven thing.
Yeah.
At that stage.
Anybody who wants to talk, just talk. Just hit the space bar.
Okay, here's a mild rabble-rousing. Some people on this Zoomokium have proposed the fun idea that Eta Carina was some sort of a in-spiral merger inside a triple system, now double. Hey, you're in Australia, just love it. I'm jealous of you. Do you have any, being an Australian, you actually know a lot about Eta Carina. Would you have any comments for whether Eta Carina is, or well, was an in-spiral for the great eruption of 1848?
Okay, so of course Noam is online right now, and he's been one of the proposers of binary mechanisms. Now, Eta Carina, as you know, is really complicated, right? There's not just in spiral, the fact that probably there's a binary there today, that the period of about 5 years is relatively stable. Now, of course, it doesn't mean it couldn't have been a triple or a quadruple in the past, and that could have maybe driven some of the behavior. Now, perhaps the complexity, Occam's razor would tell you that a behavior that complex has to have been driven by the complexity brought by a triple system, or maybe more than triple. And also, if Eta Carina's beautiful behavior was not driven by binarity, I think the universe has no sense of fun. And I think just based on that, I would say that I think there has to be an interaction between a very large and stable star and its companions playing with that instability. I can't imagine for a second that that behavior is not in great part explained by the multiplicity of the star. But I'm not an expert on the star, and I just wouldn't want to say exactly how. There's been, of course, huge controversy in the literature about just what each part of the behavior is due to what.
Maybe I can add about Eta Carina. This is Noam Soker. Eta Carina, I don't think was a third star. There are several reasons why not to have a third star, only the binary. The first one is the expectation is that if you have a third star, then you expect the outflow to be highly non-axis symmetrical. But you see the nebulae around Eta Carina, which is called the homunculus, which is quite axis symmetrical with small deviations. This is first reason. The second reason is that Eta Carina had another outburst, actually another two. One very early, several hundred years earlier, that the group of Nathan Smith claimed for, and another one that we have a record of, it was about 50 years later, in 1890 to 1895. And then you need another star to get in, and this start to be so messy and unbelievable. I think the main energy source in Eta Carina was going to a previous question about accretion. The main energy source was that mass transfer to the companion, which is also a massive star. It accreted mass in an accretion disk, through an accretion disk, and launched two jets, opposite jets that shaped the nebula. Amit Kashi, my longtime collaborator, is also here.
and he did lots of work about the Carina and the role of the jets, and maybe Amit Kashi can add something about the binary interaction there. Well, the energy source is accretion and not merger. This is an interesting case at the Carina because there was no merger, but still we have a nebula that looks in shape like that of a planetary nebula, of course, much more massive. So I'll stop here.
One thing I've never understood is that, in fact, we did one paper with Jan, who used to be a postdoc at LSU, and one of the problems is that every time that you have something in orbit that accretes in some way, and that it changes the orbit, right? So how long has the orbit been stable for? And there's some work on going back a few decades, right?
No, Amit Kashi did the calculation. Amit, maybe you can
all these
comment
things
on
have
that.
happened.
Amit did the calculation. He can comment on that.
Yes, so basically the calculation involves the transfer of mass between the two stars, as well as the mass lost from the system. And what we found is that if the orbit was a little bit shorter than today during the eruptions, about 5.1 years instead of 5.5 nowadays, then the periastron passages can actually fit the times of increase in brightness in the light curve for both the eruption in 1843 and the lesser eruption in the 1890s. So it's a delicate calculation and it has some assumptions, but it basically can you can do it with two stars. You don't actually need the third one, from the reason that Noah mentions, and also because we found that it can also explain other properties such as the fast moving material that was observed in the outer nebula, as well as other observations.
Okay.
Noam, you had mentioned in passing that there was an eruption some centuries before the 1848 big event for Eta Carina. What is your basis for that?
It's not my work, but they found material, I think, around material that is moving out around Eta Carina, and from that they deduced a previous eruption. I don't remember the details.
Brad, there's a paper, it's Kamienski and Smith, and it's archival HST observations, and you can trace back from 94 to 28 or 2016, and they estimated based on those velocities and the proper motion changes when there would have been or when there would have been eruptions in the past.
Perfect, thank you.
Anyone else have a question?
So maybe I'll ask Orsola. Orsola, you gave a nice list of arguments against the recombination energy being important in ejecting the envelope, but for it being important in the light curve. Did you put it anywhere? Is it published? Did you get comments on this?
No, so actually the reason for, in fact, the only place where I ever put together that list, which is an observationally derived list, as opposed to all the theoretical arguments you've made, is because it's only been in this talk and in the previous talk I've given, it's only in this one slide. And actually, the person who helped me, and I reference him in my slide to put this together, was Nathan himself, who is absolutely adamant that the recombination energy cannot be 100% efficient in ejecting the envelope because he studies it. You know, he's an observer and he looks at it. So I can send it to you. So no, I've never really stated it as clearly anywhere else.
Yep, I think you should put it somewhere or publish it, because I referred in my papers arguing that combination is not important, but in many cases people would like the recombination energy to explain the light curve, and you cannot use the energy twice. So I used only
I
this.
agree.
But
And so I think
you give
actually,
other arguments.
in the latest paper with Thomas, we show just, you know, how much recombination energy can work if you use it and you don't let go of it. But we also show that it doesn't, even if you do use it all, which we know is an overestimate, it still is not going to solve your problem, right? So as soon as you go to slightly more massive stars, and I'm talking about more massive as in 2 solar masses, you're not really unbinding that much. So even if it were used, it's still not going to be your solution. So the solution to this unbinding is going to be a bunch of different things, and it's probably going to be parameter dependent, meaning like massive stars do things slightly differently from less massive stars. But I think we're still a bit in the dark about this one.
Okay. So Ursula, the next Zoom is going to start at the top of the hour, and Courtney sent you an email with the phone number that you can call in.
Okay, but you know what? I might try the Zoom again. You do, and then I'll call if I have Courtney's email.
Okay.
Okay.
Yeah.
Bye. Bye, guys. Sorry about the interruption.
Wait, hang on a second. Courtney, go ahead.
All I said was either one is fine, whichever one works better.
Okay.
Okay, that's great. I got everything. Thank you.
Thanks very much, Ursula. We appreciate it.
Okay. Bye, guys.
Thank you.
Bye.
So.
Okay, thank you, everybody. We're still learning how to do this, but I still think it was a good experience.
Yeah, it could have been mainly problems down south, you know.
I think it was a problem at her house, the internet at her house.
Right. And so we are planning to have another one next week with, we'll see, but this is in the US, so hopefully there will be no interruptions, but we will see.
But I think we got most of the information across, so it's good.
Yeah. I mean, it's good. The participation was up to 58 at one point. Then, you know, it declined. Yeah.
No, but I think that's right. So we were getting up to this sort of the participation you would get at a normal colloquium.
Right.
So that was good.
Very good. Well, thank you.
Okay, I will. Thanks everybody who's left, and nice to see you, Brad. And I'm going to stop the meeting now.
Brad is still there, huh? Okay.
Bye, everybody.
Bye.
Bye-bye.